Hello, my friends. Miss Kavada here. I will not be in the rest of the week, unfortunately. So, this is an introductory video into some of the vocab you'll be using for the remainder of the week. We are going to go ahead, even though I'm not going to be there, and move forward onto our fourth unit here, being periodic trends. Hopefully, if you're watching this, you already watched the introductory video that introduces you to kind of two of the biggest trends on the periodic table with alkaline metals and alkaline earth metals reactivity. This video is going to introduce you to some of the vocab that's going to be important moving forward this week. Some of the vocab terms will be review, and then some will be new. Some of the new ones will be easy, like atomic radius, radius meaning size, and then others will be more difficult, maybe things you haven't heard of before, like electronegativity. This unit is all about trends on the periodic table, so how we can use these trends as scientists to guess or predict how things will react and bond to each other. So it's kind of actually an addition to what we talked about in the first unit when we got introduced to groups and periods. So we're going to need to remember that groups go vertically and then periods go horizontally across. But trends, think about trends like fashion trends. Right now everyone's wearing flannels or those Carhartt hats that everyone wears, or apparently now people like to wear flared leggings, which back in my day are called yoga pants. So things like that. There's trends just like that on the periodic table. However, they don't go out of style like fashion does. They are there to stick around to help us scientists make these predictions quickly instead of having to memorize everything. I do apologize. I do have a note packet ready to go for you, but I hadn't had it printed out yet. I was going to do that today. So you are going to need to do this on a separate sheet of paper. I will upload the note packet to Classroom. If you do have access to a printer and want to print it out for yourself, you're more than welcome to do that, but a separate sheet of paper will be fine. This unit is really short. It's going to take us a little longer than it was supposed to since I'm not here, because there's some labs. I promised you labs, and there are some labs we're going to do when I get back next week. So it will get extended a tiny bit, but in terms of notes, this is a really short unit. So separate sheet of paper will be fine, but I will post the note packet if you would like it as a way for some guided notes here. You will not, if you do decide to print it out, you will not fill in the whole thing today. You'll just fill in simply the definitions of all these terms. So let's go ahead and get started. This will work. All right, valence electrons. Our definition, we know valence electrons. They're electrons in the outermost or highest energy level of an atom that determine the chemical and physical properties of that atom. The reason we're kind of referring back to this in this unit is that last part there. They determine the chemical and physical properties of our atom. So valence electrons are going to be the basis of sort of all these trends, as well as atomic radius. So just to review for you, since we did have our long Thanksgiving break, valence electrons can be found using the last number in an atom's principal electron configuration, which is the one that's found on the periodic table, which we'll review in a second. But for example, with calcium, it's 2882. That last digit 2 is going to indicate that calcium has 2 valence electrons. Principal electron configuration is the simplest electron configuration, which is found on the periodic table. That includes the sum of electrons on each energy level of an atom. So we know this term as well. The dashes in between the numbers indicate a separation of energy levels. So for example, carbon, if we write out the full configuration using our orbitals, we would have 1s2, 2s2, 2p2. And if we sort of simplify that into just the energy levels, we would see the one that's on the periodic table, which is 2-4, indicating that there are 2 electrons in the first energy level and 4 electrons in the second energy level. So that tells us that there are 2 energy levels there for carbon, which is going to be important moving forward, that we can quickly identify the number of energy levels an atom has. All right, some new terms here. Coulombic attraction, which some of my friends who have taken physics may have heard of this word before, but it's the attraction between oppositely charged particles. So there's 2 sort of separate definitions with this, depending on whether we're talking about within an atom or between 2 atoms. So if we're talking about within an atom, it's the attraction between the nucleus and an atom's that should not say protons, that should say electrons, sorry, fix that. So nucleus and then atoms, ignore that, should say electrons. Larger atoms experience less attraction to their own valence electrons because they are further away from the nucleus. So there's more crowding going on. The more layers we have, the more energy levels we have, the harder it is for that nucleus to be attracted to its own electrons. Then between atoms, if they're bonding, it's the attraction between the protons in one atom, so the nucleus of an atom, and the electrons of another atom. So bonding, we'll get to that in 2 units. Bonding is going to be all about that kind of attraction. So for right now, we're more focused on the first bullet there being within an atom and its attraction between the nucleus and atoms, again, that should say electrons. All right, let me go back. The reason we need to talk about that is because this is also sort of the basis of all these trends. So the 3 important things are going to be the valence electrons and energy levels, Coulombic attraction, because this will be the driving force of all the trends, and then this one here, atomic radius, which is kind of what it sounds like. It's the distance measured in picometers from an atom's nucleus to its own valence electrons. These are all found on table S. If you go to table S, I'll give you some examples. Here are atomic radius. So it's literally just the size of an atom. Here is an example of sort of the trend that you will be studying. So you may actually want to come back to this slide later this week. This does a really good job of showing you what the trend is going across a period and what it is going down a group, which I'm not going to touch on yet, but you will learn this week. Ionization energy is a new term. It's the energy required in kilojoules per mole to remove an electron from an atom. So how easily or hard it will be to take an electron away from an atom. So for instance, taking hydrogen's 1 electron away. The values are also found on table S. It's the first ionization energy that is on table S there. That's kind of the one we care about the most. And as we get towards our halogens, it's going to get more difficult. And again, you'll see that trend as you study it later on this week. So for right now, all we need is the definition. Electronegativity is a measure on a scale of 0 to 4 for how strongly an atom can attract electrons to itself from other atoms. These values are also on table S in the reference table. Fluorine has the highest electronegativity value of 4.0, and we will notice that the noble gases, so for instance helium here, has no value because they already have 8 valence electrons, so why would they need to attract any electrons to themselves? So they're going to have no value or a value of 0 for that, okay? Ionic radius is the size of an ion when an atom has either gained or lost electrons. So some types of ions that we have here, some new words. A cation is when an atom has lost electrons and becomes positively charged, and therefore its ion has a smaller radius than the atom. So for instance, calcium going to calcium plus 2. An anion, like an onion, which would make you cry, is when an atom has gained electrons, so it's gaining negativity. It becomes negatively charged, and therefore the ion will have a larger radius. So for instance, fluorine gaining an electron to become fluorine minus 1. So cations, think about cats. They're positive, so they're becoming positively charged by losing an electron. Anions are like onions, and they make you cry because they're gaining negative charge. Here's an example of like a sodium atom going to a sodium ion. We see that the sodium atom here has this 3rd energy level. And then if we jump over here, when it loses its electron, it loses an entire energy level. So it gets much smaller. Here's a good example of atom sizes versus their ion size. Again, you might want to refer back to this later this week when you are studying the trends a little bit more. So I won't go into too much detail on this, but this is a good image for reference later on. Metallic character is the level of reactivity of a metal. Metals tend to lose electrons in a chemical reaction due to their low ionization energies. So how easily it is for them to lose an electron. This makes sense because metal ions, they have 1 or 2 valence electrons. So it's typically, or 3 maybe. So it's much easier for them to lose 1 or 2 than to try to gain a lot of them. Like for calcium, they would have to gain 6 electrons to get to 8, which would make it have its maximum stability. So it's easier for calcium to lose those 2 electrons and lose an entire energy level rather than try to gain 6 to become 2888, like that. To get, again, we want to get to maximum stability using the least amount of energy. This term is not on the notes because it's literally the opposite of metallic character, but I just wanted to go over it. It's the level of reactivity of a nonmetal. So nonmetals, we know, tend to gain electrons because they have high ionization energies. It's much easier for a nonmetal to gain 1 or 2 valence electrons rather than trying to lose multiple. So for instance, chlorine here, we have 287. If it becomes chlorine minus 1, it very easily becomes 288. So it'd be much easier for chlorine to just gain 1 more than to try to lose 7 electrons to jump down to this energy level that already has 8. Okay, so you only need to write down metallic character because once we understand that, then we would very easily understand non-metallic character. But again, since I'm not there, I just wanted to go over this, the difference between the two. So make sure in your notes you're writing down the definitions, and I would highly suggest writing down the examples I have in each slide as well, and maybe even when you are doing the atomic radius, writing down a few examples, so maybe drawing a few examples with circles in your notes, and then also with ionic radius, maybe writing down this example with sodium or writing down a few of these examples here from this picture. Okay, because you're going to come back to these notes and you're going to add on them the trends going down a group and across a period later on this week. All right, I will miss all of you. You need to, every day, make sure you have a charged Chromebook and headphones because you'll be watching a lot of videos, unfortunately, of either me teaching you things or other videos I've found on YouTube that have already been made. And you'll also really want your reference table because a lot of this stuff is on table S. So I'm teaching you these trends because it makes things much easier, but a lot of these trends you can figure out by just looking up the values of different elements on the periodic table. So you'll see we have first ionization energy, electronegativity, and atomic radius already on table S for us. All right, I will be checking my email, so if you have any questions, I'll try my best to answer them over email, and if not, I will see you a week from Monday. Thank you. Have a good week. Be good to the subs. Bye.